The logical progression from cylindrical coordinates would be, of course, moving on to spherical coordinates. So let's talk about the idea of just how we're going to evaluate triple integrals in spherical coordinates and just exactly what the thing means. Now, in rectangular coordinates, we had obviously a rectangle. And then in polar coordinates, we ended up with a polar rectangle. And now in spherical coordinates, we're going to actually end up with spherical wedges. So first, let's just do a very quick review of the idea of spherical coordinates. We have an idea what we're talking about here. So I have a point up here, which I could represent obviously with x, y, and z coordinates. If I take a look at, just like we did cylindrical coordinates, I'll look at this projection of this point, get rid of that part of the axes, onto the xy axis. Then, reminiscent of polar coordinates, I'm going to have this angle theta. And rather than rho being here, or r being here, I'm sorry, I'm thinking now as this is being my radius, which, I'm sorry, we're going to write as rho rather than r. And I also have this angle between the z-axis and rho, which I'm going to make reference as phi. So this point, xyz, I can write as the point rho theta phi. Now, what this does for us in terms of translating from rectangular to spherical coordinates, x, y, and z, we'll now have x, and you can see from the diagram that's going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta, and z is going to be rho times cosine of phi. Oops, this is sine phi. I think I said phi and wrote theta. Sorry. That needs to be phi. So let's take a look at this wedge in 3 space. Okay, so rather than putting you through the misery of watching me struggle trying to draw this thing, I paused you. I went ahead and drew something that kind of looks like a wedge up there floating around in 3 space, and this is what we're going to work with. So when I look at this thing in 3 space, think of this projection here of actually coming together to the origin. So with that, I can think about how angles are changing. This angle, let me do this in red. This angle here in red, I'm going to think of as being delta theta, because theta is changing on the xy plane, and this is a horizontal change. And the switch to blue, say this angle here, I'm going to think of this as being delta phi, and with that I can define all these edges on this wedge. Now the distance here, that's going to be delta rho. This is actually an arc length, and this arc length, come over here and write it, will actually be, say, rho I sine, sine of phi k, and then delta theta. So I drew this big wedge, but think about this now as a smaller wedge inside here. So pretend for a moment that this got this big wedge, and we're going to break this up into sub wedges, just like we broke up the rectangular regions into sub rectangles. So this is describing a particular rho I sine phi k in a wedge E I J K. So this is the ijkth wedge. Now this is going to describe this arc length right here. Whereas this arc length I can describe as simply being rho I times delta phi. So if I look at the ijkth sub wedge EIJK, it's approximately a rectangle. So in 3 dimensions. So the area can be, or the dimensions, which I can use to calculate the approximate volume for the that particular sub wedge, I can write as delta rho times rho I delta phi times rho I sine phi k delta theta, which is going to be rho I squared sine phi k delta rho delta theta delta phi. Now, just so you understand where these came from, this angle change here we said was delta phi, and if I take the radius and multiply it by the radians of the angle that I travel, that gives me the arc length, because this is actually an arc length. And then this one is the exact same thing, but the question here is, what is the radius here? What is the radius to multiply by this arc length, or by this change in angle? Well, this angle has a projection down the xy plane, and that's what we think of as being theta. But I'm claiming that this distance is rho I sine phi k, which, if I draw a quick triangle here to represent this, say this is the this is rho reaching out and touching that point over here, and this is the angle phi. So this is rho. Then sine of phi is going to equal this distance, wherever this is, over rho, which means that rho sine phi is equal to this distance here. Well, actually, it's not this distance. Let me grab another color. It's actually this is. I'm thinking this being horizontal to the xy plane, so it's really this distance I'm looking at going across. These are actually parallel lines. So this distance times the change in the angle is what's going to give me my arc length, essentially. Because this angle here, I can actually think of this is phi right here. Now, with this, we can approximate the total area with a triple Riemann sum that would look like the sum I equals 1 to L, the sum J equals 1 to M, the sum K equals 1 to N of this function f, which is going to be rho I, the function of rho I sine phi k cosine theta j. This is just x. This is a function of x, y, and z. And there's x as spherical coordinates. Rho I sine phi sine theta. This is going to be k and j. Oops, small j. And then z is rho I cosine phi k. Again, that's x. This is actually just y. And this is actually just z. And then all this could be multiplied down here. So I'm going to need my rho I squared sine phi k delta rho delta theta delta phi. Now that, obviously, when we take it in the limit, this will actually bring us to the formula for a triple integral in spherical coordinates, which is the triple integral over E of f of x, y, z dv is equal to the integral from c to d, integral from alpha to beta, the integral from a to b of f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi, rho squared d rho d theta d phi, where E, this E, is the spherical wedge, or a spherical wedge, defined by E equals the set rho theta phi such that A is less than or equal to rho, which is less than or equal to B. Alpha is less than or equal to theta, which is less than or equal to beta. And C is less than or equal to phi, which is less than or equal to D. Now, if we're working with something that is well modeled by a spherical wedge, then this transformation can be well worth it. It can be extremely awkward to integrate functions that lend itself well to this if you don't make that transformation.